Welcome back, viewers. Have you ever encountered questions like in a school, there are some people who play football, and then there are some people who play cricket, and then there are some people who play both football and cricket, and you have to deal with those kind of a situation, and you make sets and you make Venn diagrams, and you use certain formulas there. And today in this video, I'll be going to generalize that that formula which you are using, and you might have seen the proof for 2 or 3 sets, and you but today I will discuss whether it will work for 4 sets, and in more general case, like for any number of sets, how would that formula look like, and would it work or not, how to. So that thing is called inclusion exclusion principle. So for 2 sets, it goes like this: you have these 2 sets and you have some intersection of these 2 sets, and then you have a certain number of elements in only in set 1, and then certain number of elements in both 1 and 2, and then certain number of elements only in x2, right? So then you use this formula to calculate these elements in the union of set 1 and 2. By union, which means like it's in either in set 1 or in set 2. So you have, in that way, like speaking in these terms, you have to sum all these numbers. And when you do that, so this is the union, you have to sum all these numbers: 1, 1, 2, and 2. Notice x1 is only this part of the diagram. Okay, x2 is only this part of the diagram, the number of elements only in set 2, right? But a1 as a set, it's this complete circle, right? It contains x1 plus x12. The number of elements in a1 is not only x1. X1 is the number of elements which is only in the set a1, but not in set a2. So if you're writing this term, then you have to be careful. So you have to write x1 plus x12, right? So this area is, sometimes I will say the number of elements as area. This area is x1 plus x12. Then the second area in the formula is x12 plus x2. And then the third area, which is the intersection, which is in both of these sets, and that would be x12. So if you do that, you see when you added x1 and x12 with x12 and x2, you had x1, but you had x12 twice, right? So you had x2 once, you had x1 once, but this thing you added twice, and you need to subtract it once, and it got subtracted with this term, and that's why this formula works. Fair enough. So for 3 sets, this formula becomes something like, we'll see, but the number of elements, you see we have so many different kind of areas here. We have x1 denoting the area which is only in a1, and x2 denoting the area only in a2, and x3 only in a3, and then you have some areas like x12. This is a very interesting area. x12 is not the intersection of a1 and a2, right? Because intersection of a1 and a2 is this complete area, but this is not what I mean when I write x12. I mean the area which is in a1 and a2 but not in a3. a1 intersection a2 and intersection with a3 bar, okay, not in a3. This is how it's simpler to define variables, because if I use x12 for this whole area, then I will not get mutually exhaustive, mutually exclusive areas, if you know what I mean. So this is a very interesting kind of an area. This is also a very interesting kind of an area. This is the area which is in a2 and a3 but not in a1. And then similarly 1 3 is also that kind of an area. And at last I have an area which is in all of these sets, and this completes the diagram. And the formula for the union goes like this: This is not random. At first sight, you might feel that this is random maybe, but even when I was a kid and I saw this formula for the first time, I could see the pattern. So the pattern is like you're summing the areas, the individual areas in individual sets A1 and A2 and A3, and then you are doing a subtraction of intersection areas. And now when I take this intersection, I mean this whole thing, like A1 and A2, the intersection of A1 and A2, I mean this whole area. Small details, but very important. So I mean this whole area. So this thing we are subtracting for all all the sets taken two at a time. So that intersection area we are subtracting, and then we see that there is a plus sign. So there is an alternating plus minus kind of a situation happening, and the intersection and the number of intersection of sets is increasing in each step, right? So what do I mean? This is your step one. It's not like a step one. You can say that this is level one, and this is level 2 of the formula, and this is level 3 of the formula. Okay, so let's check whether it works or not. It could be simplified as this level as this, and this level as this. Let's see whether it works or not. So when you are taking NA1, you are taking all these x's. Then when you are taking NA2, you are taking all these x's. So already you see that some of them are getting added twice, but that would be accounted for later in the formula. When you take A3, then you take all the x's with 3 in them. When you subtract A1, A2, you are subtracting all the x's with 1 and 2 in them. So you subtract 1, 2 and 1, 2, 3, right? This you can figure out from the diagram also. When you are subtracting A2, A3, the intersection of A2 and A3, you are subtracting this term and that term. So first of all, when you are exploring, you should do it on your own, and you should see how it is happening. You should not rush to the result, because when you see, you might discover something new. So please verify it on your own, and when you see that, when you complete the formula and sum them, you see things cancel out and it turns out to be correct. So it turns out to be all these x's here, and that too only once, and nothing is subtracted, everything is getting added once. So it fits in a very beautiful way. Okay, so for 2 sets we had this formula. For 3 sets, which could be written in like 2 levels, one first and second level. For 3 sets, the formula would have 3 levels, first and second, and in the third level you have a plus sign. Alternating plus and minus is happening. So for 4 sets, it should go like you first add level 1, and then in level 2 you subtract this intersection of 2 sets, and in level 3 you add intersection of 3 sets, and in level 4 you subtract the intersection of 4 sets, and there would be only one such term, so I don't need to write a summation here. Anyways, and in the general case, well, this formula should look like this, but this is just an hypothesis till now. This is also a hypothesis till now, because we haven't proved that it would work. So our minds can sometimes think some things on the basis of past things, and they turn out to be wrong. For example, it's very famous, very famously said by David Hume, that the sun will rise tomorrow is only a hypothesis. I don't know whether it was David Hume or Wittgenstein, but yeah. So we don't have a proof for, we saw this happening for 2 sets, for 3 sets, we'll see this for 4 sets, and in the general case for n sets, this will also work. So I'll show you how. Does it work for 4 sets? So for 4 sets, let's draw the Venn diagram. But how? We have been drawing Venn diagrams with circles. And for 3 sets we have this kind of a Venn diagram, and we include the 4th circle, and the 4th set I need to intersect this 4th circle in all possible ways. So let's bring it more closer, and you think that this is the Venn diagram we are looking for, but let me show you this is not true, because you have some areas, like you have the green set, you have the blue set, and the red set, and the orange set, and this G here is denoting the area which is only in the green set. Then you have the area B which is only in the blue set. Then you have area which is only in the red set. You have area which is only in the orange set. Okay, then you must have all the areas which are in 2 sets exactly. For example, you have a green and blue kind of an area which is only in the green and blue set. Perfect. You have a green and orange kind of an area which is only in the green and the orange set. It's not in the red. You see, it's outside red, and it's also outside blue. Great. How about, do we have a green red? Take a look at it. We don't have a green red in this diagram, because this area here which is in green and red is also in orange, right? So this area here is green, red, orange. Okay, so this area here which is in green and red circles, but this is green, red, orange, blue kind of an area, and this area here, that's green, red, and blue. So we don't have exclusively the green red area here. Okay, so maybe we can adjust it a little bit, and now we can have the green red area. Fine. Okay, how about B, blue orange area? Do we have a blue orange area? Take a look at it, pause the video, take a look at it. I don't think that's there. Basically, you can't draw a complete Venn diagram showing all the intersections with 4 same sized circles. I am not sure about this fact also, but intuitively I have a feeling that it's not possible. Maybe you can say that if I change the size of the circle, then I can do it. You can try for it, but I feel, I looked into this question for a little while, and I felt that it's not possible, perhaps because that's why people are using different kind of a notation. But this is also very interesting. There are 170, around 170 ways in which 4 circles can intersect. I will share a link in the description for that amazing picture in which you can see all those possibilities. And there is a numberphile video also about this thing which I'm talking about. I'll share the link of that video also in the description. But that doesn't gives you the proof that it's not, that doesn't talk about Venn diagrams. Anyways, so what's wrong with this picture? Like, why it's not able to account for all the possible areas? Because how many areas do we have in Venn diagrams of 2 sets or n 3 sets and n sets, generalizing that thing? So how many different kind of areas are possible in 2 sets? So in 2 sets you have 3 different areas, right? These 3 different areas, and these areas are non-exclusive, non-inclusive, exclusive areas. We have 3 exclusive areas like these, right? So A1, A2, and A1, 2. For in 3 sets we have A1, 2, 3, and these 3 areas, and then so 3, 3, 6, and 7 areas. So what is the pattern here? How many such areas do we need in a Venn diagram of 4 sets? So let's think about that. In the 3 set, you had these first 3 areas can be understood as like selecting the number of ways in which you can select 1, 2, and 3. Okay, only one. Okay, only one out of 1, 2, and 3. So let's say there are 3 sets, S1, S2, and S3. If you pick up 1, it means that you are thinking about an area which is only in S1. If you pick up 2, then you are thinking about an area which is only in S2. And if you pick up 3, you are thinking about an area which is only in set 3. So there will be 3 such ways. And when you are selecting 2 numbers out of 1, 2, 3, suppose you select 1, 2, then you are thinking about this area, of course, 1 which is only in 1 and 2. Right? So that way we can count the number of possible areas. And so the number of ways of selecting 2 numbers out of 1, 2, 3 would be 3. And the number of ways of selecting three numbers would be 1, 2, 3. And this way you see that you get the right sum, 3 plus 3 plus 1, 7. But it's not about the number, it's about the structure. So total you have 3C1 plus 3C2 plus 3C3. And you can add a 3C0 for completeness and subtract a 3C0. And then you see that it should be, this term should be 2 to the power 3 and this minus 1 more, and you will get sorry, here I haven't shown minus 3C0, but yeah, that's obviously missing. But anyways, we have the number 7, 2 to the power 3 minus 1. You can generalize for n sets, that should be 2 to the power n minus 1, right? So for 4 sets you should have so many like 2 to the power 4 minus 1, which is 15 different areas you need to have. And in that kind of a Venn diagram, when you are drawing with 4 circles, let me show you here, like these Venn diagrams, you had how many areas? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is not 15. So we don't have 15 areas here. So we can't this Venn diagram is not going to cover all the details. So what is the Venn diagram which will do that? Is this beautiful picture with ellipses. It's the simplest one which I could use. So with ellipses, now you see you have 1, 2, 3, 4. This is S1, the green one is set 1, the blue one is set 2, the red one is set 3, and the gray one is set 4. And you have these areas which are only in the respective sets 1, 2, 3, and 4. So that's there, and you have these 4 areas. Then you have these 6 areas 4C2, like which are in 1, 2, 2, 3, 3, 4, like that. So you have these 6 areas there also. Take a look at it. You might see something new. Don't go just by my words. Maybe pause the video, come back again. This is a marathon video, so it's very important for you to take a look at it on your own. So you have these 6 areas also there, and the number of ways of selecting 3 numbers out of 1, 2, 3, 4, that would be there would be 4 such ways, right? And those 4 such areas are also there, right? And finally you have that area 1, 2, 3, 4, which is also there, and you sum it up, and that would be 15. Fine. So what is the area which we are going to verify here is that if you use this if you have to find out the union, number of sets in the union of all these 4 sets, our previous formula extrapolates to this thing. Well, how on earth are we going to check it? We're not going to write it down one by one like we did for 3 sets, which was done because that was not so complicated. So now we will do it in a shorter way. So what the idea is, like any of these area, like 1, 3 or 1, 3, 4 or 1. So when you do this sum, any of these areas should be accounted for plus 1 times, only 1 times, not twice, not negative times, only plus 1 times. Okay, so for example, let's say it's like 2, 3. So 2, 3, when you are summing in the first level, 2, 3 will be summed how many times? I think 2 times, because when you are summing this second set, the area inside the second set, you encounter 2, 3 once, and when you are summing the area of the third set, you encounter this 2, 3 there also. So you will encounter it 2 times, so plus 2 times. But in the next level, when you are subtracting the intersection of 2 sets, 2, 3 will be encountered only once, when you will be subtracting the intersection of 2 and 3. So this is your second set, this is your third set, and their intersection, where is their intersection? Here. In that there is 2, 3. So that 2, 3 will be subtracted once also. and this will give you a final sum of 1, because in the later sums, in the later levels, 2 3 won't be encountered, because 2 3 is only in set 2 and 3, and in the later sections you are summing the sum, you are accounting for intersection of more sets. Okay, then let's think about 1 3 4. So in the first level you will encounter it 3 times in the set 1 3 and 4, and in the second level, how many times? So I think that would be 3C 2 times, because you have 1 3 4, and if you select 2 out of this 1 3 and 4, like 1 3 or 3 4 or 1 4, right? So that would be 3 times. In a simpler way you can write 3C 2. So minus 3 times, plus 3 minus 3, it's gone, but there is one more level in which it will be encountered, and in the third level it will be encountered only once, and this level is a positive level. It will be added plus 1, and you will get it plus 1 times. How about 1 2 3 4? You can do it as an exercise. 4 times, 4C 2 times minus 6 times, and 4C 3 times added plus 4 times, and 4C 4 times subtracted minus 1 time, and that also turns out to be 1. So I think you should begin to see that this formula is working for not only for 4, this is going to work for any case, for any n number of sets, if you use this logic. You don't have to do the complete algebra. Okay, so let's generalize this. You have n sets. I can't draw the Venn diagram for n sets, but we understand this is the formula which we are checking here. In a way, there is a very interesting thing which I would like to share here. I am only verifying a formula, and which seems like it's the proof, which is a proof in a way, if you verify that it will work. So, but I am using something, there is an element of induction, mathematical induction involved in this proof. So what I wish to see is that I don't have an insight into the original thing which is giving rise to this formula. I am just extrapolating and verifying. So there's something which is hidden here for me, and if you know it, then please share with me in the comments that original insight into this formula. Anyways, so here you will have many different kind of elements like 2 3 1 3 4, and now you can have a large number of sets. You can also have, let's say, set 23rd. So I should use brackets to denote such areas. I can also have this 1 2 3 till n kind of an area, which will be the intersection of all these sets. I can also have this kind of a 7 6 and then n minus 1, but you should notice that I shouldn't write 7 before 6, because then that would be confusing. It's better to write in increasing order. So this is not a nice way of writing it. What I'm saying is, like, if you have an area which is in 7th, 2nd, 4th and 5th set only, then you can write it better as 2 4 5 7, the area number 2 4 5 7, rather than 7 2 4 5. Arrange it in increasing order, arrange the digits and put a bracket, because this, somebody could have thought that this is 24 57, but it's not like that. So anyways, in general, a general such area is like A1 A2 A3 AK. Not saying this is 1 2 3 till k, that would be a particular area. I'm talking about a general area. A1 could be any number. Okay, so this is a general area which will be in set SA1 and set SA2 and then set SA3 and set SAK only. This is interesting. So we have to be precise while speaking what I mean. Anyways, so this area, if we are summing in the first level, if we are summing this part, how many times will we encounter this area? K times, and it will be added plus k times, right? Then in the second part, it will be subtracted how many times? Pause the video, think about it, and the answer is minus kc2. And then in the third level, it will be added kc 3 times, and then you see that k can be better written as kc1. Yeah, and then you proceed on till the last level and you get this term, which will be positive or negative depending upon the number of sets. And what is this sum? This sum should be plus 1, right? And it is plus 1. It's not very difficult to see that it is plus 1, because you see this binomial expansion, these binomial coefficients are very common. And you see this binomial expansion of 1 plus x to the power k, and you put x is equal to minus 1, you get this term here. So this part becomes 0, this thing is 1, and you get this sum. It's negative here. So you put this part here on the left hand side, and you will see that this the thing which we are looking for is positive 1. Hence proved. Thank you very much for watching this video, and now you can very confidently use principle of inclusion exclusion anywhere in your calculations. Thank you.